Hello dear students, welcome to our Vision Pharmacy. In our today's video, we will be discussing an important topic from Physical Pharmaceutics, that is liquid complexes, which comes under the chapter States and Properties of Matter. So before we start, please do like, share, subscribe and press the bell icon for getting updates on upcoming videos. Let's begin dear students. So starting with definition. A liquid complex is a homogeneous liquid formed due to interaction between two or more components, often solute and solvent, where coordination or complex formation occurs in the liquid state. So students, remember that a liquid complex is a homogeneous liquid mixture where molecules or ions interact to form a coordinate or associate structure. Okay? The complex often shows different physical properties like that of boiling point, viscosity, conductivity compared to individual components. That is, unlike ordinary solution, here a true complex is formed, right? So which results into showing different individual properties. Then these are commonly seen in pharmaceutical formulation where solute-solvent interactions play a vital role. Okay, so the last point says that is common in pharmaceutical solutions and liquid formulations. Moving to the next slide. So students, here you can see a diagrammatic representation of the various liquid complex formation with liquid as a solute and then reacting with other components. So there could be a reaction between liquid solid, liquid gas, liquid liquid, etc. Okay. Then moving further, basic concept of complex formation. So students, basically complex formation occur due to Lewis acid-base interaction or donor-acceptor interaction between molecules or ions. So complex formation occurs when one molecule or ion donates an electron pair and another accepts it. That is what we call it as Lewis acid-base interaction. The main forces involved are electrostatic attraction, then hydrogen bonding, van der Waals forces, or coordinate covalent bonding. Okay, so for example, the ferric ion and thiocyanate ion forms a red colored, that is FeSCN2 plus complex. Okay, so the complex formed is basically an association due to these attractive forces. Moving further, classification of liquid complexes. So basically, this liquid can be classified into four main types. The first one is molecular complex. So it has a very weak interactions like that of hydrogen bonding, and the example of this is caffeine chloroform complex. Then the second one, that is the ionic complexes. This is an association between ions and the example is Fe3 plus and SCN minus. Already we have seen the ferric ion and thiocyanate ion. Then moving to next one, that is charge transfer complex. Here the result is of donor acceptor interaction where an electron cloud is partially or partly shared, such as iodine with aromatic hydrocarbons. And moving to the last one, that is metal ligand complexes. Here a true coordination bond occurs. Example, copper ion with ammonia. So each type differs in the strength of interaction and the stability of the complex. After classification, we will try to study the characteristics of liquid complexes. So the liquid complexes have a unique measurable properties. That is, there they exhibit different refractive index, conductivity and boiling points. It means that the refractive index, boiling point and conductivity are usually deviate from their ideal behavior. Then the second point is they often show color change due to electronic transition. The next point states that may show non-ideal behavior in Raoult's law. The next point is reversible or irreversible formation. So students, the formation may be reversible or irreversible depending upon the strength of the bonding. Then the next one is some complexes are highly stable. Okay, that is when complexation occur, the stability of the system often increases. So it's directly proportional to that of the degree of coordination. Moving to the next point. So next point is mechanism of formation. So the various mechanisms which are involved in this complex formation include first one, that is hydrogen bonding. Example, phenol with pyridine or alcohol. The next one is pi-pi interaction. So this type occurs in aromatic rings. Okay. Then moving to the third one, that is dipole-dipole or van der Waals attraction. Then the next one is metal coordination, that is a lone pair donates to a metal ion. Then the last one, that is the fifth type, is proton transfer, which occurs in acid base system. Getting? So the strength of interaction is directly proportional to polarity and donor ability of the molecules involved. Now, after knowing the mechanism, we will be seeing the factors which influence or factors affecting the complex formation. So, several factors influence complex formation. Some of the factors include temperature. Usually, if complexation is exothermic, increasing temperature decreases stability, that is inverse relation. Then the next one is concentration of components. So higher concentration of reactants increases complex formation until saturation, that is they are directly proportional to each other. Then the third one is pH of the medium. So it alters ionization and optimum pH favors complexation. Then the next point is dielectric constant of solvent. So students, lower dielectric constants enhances ion pairing, thus irreversibly proportional to that of the polarity. And the next one is presence of other ions or molecules. So students, if there exists a competing ion, so ultimately it will result into decrease in formation of we can call it as shifting equilibrium. Okay, so it is irreversibly proportional. Moving to the next point, that is pharmaceutical significance. So talking about pharmaceutical significance, the points included are first one, improves solubility. Example, caffeine chloroform complex. Okay, so these complexation can improve drug solubility. Moving to the next one, that is drug stabilization. It reduces volatility or degradation. Okay, so it can stabilize volatile or easily oxidizing drug. Then the next point is taste masking, that is formation of complexes with cyclodextrin. Okay, so complexes helps in taste masking as which of cyclodextrins. Then the next one is control release formulation. Some complexes are used for control release. Then the next significance is gelatin therapy. That is, in this therapy, complexes helps to remove toxic metals. Okay. So this was all about the liquid complexes, students. To summarize, liquid complexes form through high specific molecular interaction in liquid state. Their formation and stability depends upon several physical factors, and their understanding helps us to design more effective, stable and acceptable pharmaceutical formulation. So that's all, students, in our today's video. Thank you for watching till end.